and I'm with the National Ocean Sciences Bowl, the national office in Washington, D.C., and I'm glad to welcome you to today's webinar. Each year we hold these webinars specifically on topics related to our competition theme, and for 2019, we're focusing on ocean observing. Our official title is Observe the Ocean, Secure the Future. The idea is to show you just how ocean observing is used by scientists to help us secure our future at everything from, as you'll see today, what kind of observations can be made to assist us in knowing what's going on the seafloor, to fishing and security, our food supply, and also just sort of understanding the general conditions of the ocean and how much they're changing, because we know they're changing faster than we realize in most instances. So today's webinar, just so you know, is going to be about an hour presentation, and then we will have 30 minutes for a Q&A session. So you'll notice that everyone who's on the webinar today, we have you muted. That's simply so that we're not going to disturb the presenter with background noise. So you will see that there is a chat box. That is where you're going to type in your questions if you have any. Feel free to type them in as the presentation goes. For the most part, we're going to save all questions unless they're really timely during the presentation. We'll save all the questions to the end, and we'll have about a 30-minute period for those questions. I will read them aloud to our speaker today, and then she will answer them. So again, at any time, feel free to use that chat box. So today, I'd like to introduce our guest expert. It's Haley Cabaniss, and she is a PhD candidate in the geology department at the University of Illinois. And she's actually going to present on something that I think is really interesting and possibly a use for ocean observing that you haven't necessarily thought of before. She's going to talk about how she uses ocean observations to forecast undersea volcanic eruptions. So I'm going to turn it over to her. And again, feel free to type in any questions you have into that little chat box. Okay? Haley, if you'd like to start, go right ahead.
All right. Thank you so much, Melissa. So I really appreciate all of you taking the time to participate in the webinar today. And I'm really honored to have been asked by the Consortium for Ocean Leadership to discuss my research with you. So as Melissa mentioned, my name is Haley Cabaniss, and I'm a PhD candidate at the University of Illinois Urbana-Champaign, where I'm using numerical modeling as a tool to study volcanic eruptions occurring on the seafloor. I'll get into how and why a graduate student living in the middle of the country can participate in that kind of research. But first, I do want to mention to you, let's see, all right, sorry about that. We know more about the surface of some planets than we do about the Earth's seafloor. And as much as I would like to attribute this quote to one individual scientist, it's really difficult for me to do that because I've heard every scientist in my field use it at some point or another. But it's true. We've mapped about 98% of the surface of Venus at a resolution of about 100 meters. Mars and the Moon are both mapped at 100-meter resolution, and even portions of the Moon are mapped at 7-meter resolution. But when we look at the Earth's seafloor, we know that 100% of our seafloor is only mapped at kilometer-scale resolution. About 10 to 15% of the ocean floor is mapped at 100-meter resolution, like these other bodies, and 0.05% of the ocean floor is mapped at meter-scale resolution. And this is important for a number of reasons, notably that undersea cables transport a lot of our international data. So I imagine that these can be issues of trade and international security and general communication and navigation information. We also know that there are valuable resources in the seafloor that can be used to enhance technology. And of those resources, we know that there are things that can be used to treat ailments like cancer. Now, selfishly, I want to tell you that we're learning a lot about terrestrial volcanic systems, about how and why they erupt, and even how to forecast them from underwater volcanic systems. And that's going to largely be the focus of our talk today. But I do kind of want to go through a brief history of seafloor observations, A, because I think it's important, but B, so that you have some understanding of why we know what we know about the Earth's seafloor. So I'm going to start by talking a little bit about the history of seafloor mapping, because that's ultimately where our journey of discovery in the seafloor begins. So Some of the earliest mapping techniques were those of line and sinker sounding methods. So basically a lead weight is tied to the end of a hemp rope, and this can be hundreds of pounds. And it's lowered into the ocean until you feel slack in the line, and that was an indicator that the lead weight was on the seafloor. The slack that was paid out into the line was then measured and used to estimate the depth to the seafloor. And there's evidence of this technique being used as early as by ancient Greeks and Romans in the Mediterranean Sea. A few centuries later, a version of this approach replaced the hemp rope with a wire, which improved measurements slightly by removing some of the effect of that hemp rope drifting in the water. And the piano wire method, as it was called, also decreased the amount of time it took to make such a measurement and allowed for more measurements to be taken on a given expedition. So here, can you guys see my mouse? I think you can. So you can see kind of the conceptual diagram for that piano wire sounding method and some people using it out at sea to map the seafloor. So even though this technology made it a little bit easier to collect soundings at sea, the earliest maps made using these methods suffered pretty greatly in their resolution, just given the amount of time it took to collect those measurements. And in fact, this map in the lower right-hand corner was made using these techniques, and while it is the first map to show kind of the continuous nature of the mid-ocean ridge system, it fails to identify some large to intermediate scale structures in the ocean floor. All right, now at the end of the 1800s, increased ship traffic and the use of submarines in warfare raised navigational concerns, which prompted the invention of a new early detection system for objects in the water. Sonar, which is an acronym for sound, navigation, and ranging, made use of underwater acoustics for these purposes. So a new system was developed in which underwater bells were placed on objects of concern, such as lighthouse, and they were used to alert ships outfitted with listening devices known as a hydrophone. Unfortunately, hydrophones were really helpful in determining the distance to an object, but not necessarily the direction in which the object was located. And these devices also picked up on a lot of background noise and weren't alerting ships in time to necessarily avoid a collision as a result. So the sinking of the Titanic in 1912 kind of reinforced the need for a new detection system. And a year later, the first prototype of a single beam echo sounder called the Fessenden oscillator was created. So this device was able to not only hear sound, but to transmit and receive it for the purposes of estimating depth or distance. Echo sounders were then rapidly implemented on ships and submarines alike to detect not only for unanticipated natural objects in the water, such as icebergs, but quite commonly for submarines. So these instruments were used largely for navigation and warfare until the early 1920s, when they were first used to map the South Atlantic Ocean. So I want to mention that Earth science started moving really rapidly once sonar became common practice in science. And this map was published in 1977. It's the first map to show all of the Earth's ocean basins, and it was largely based on decades of work done by Marie Tharp and her partner Bruce Heezen. So Marie Tharp's maps drove the discovery of plate tectonics. She discovered an axial valley atop the mid-ocean ridge system. Where's my mouse? And she even linked the location of earthquakes to the mid-ocean ridges. And she actually suggested some of the concepts that were later published in Harry Hess's famous paper, A History of Ocean Basins, who at the time was kind of angered by the work that Marie was doing and actually chalked it up to girl talk. So I always talk about Marie when I give a talk about the oceans, just because she was not necessarily given credit for her earlier work, but she was a very prominent figure in understanding the ocean floor and also understanding plate tectonic theory. All right. Oh, and also, I've put a cover of a book here. This book, Soundings, is incredible. If you're interested in the plate tectonic revolution or Marie's life or how we first started mapping the seafloor, I highly recommend reading this book. It was wonderful. All right. So we've continued to build a lot off of the advancements of the early 1900s, and we're still actually using this technology, albeit in a more sophisticated form, to map the seafloor. And in fact, today, using multi-beam sonar is the most common way to map. This is done by measuring the two-way travel time of sound transmitting from the ship to the seafloor and back to the ship. So if we know certain properties of the seawater, we can estimate the speed of sound in water and use that information to determine the water's depth, and thus we can calculate the bathymetry of the seafloor. The resolution of this technique for mapping is highly dependent on the water depth, the survey design, and of course on weather conditions, and it can be used to map at the scale of just meters or hundreds of meters. And ironically enough, the resolution of this technique is high enough that we can even use it to map pre-sonar shipwrecks. I'll remind you that shipwrecks and navigational concerns were one of the reasons that we started using sonar in the first place. So multi-beam sonar is the technique that we've used to map 10 to 15% of the Earth's oceans at 100-meter resolution. So how have we mapped the additional 85% of the oceans? All right, so I mentioned earlier that 100% of the seafloor is mapped at a resolution of about 1 to 2 kilometers. Some satellites can be used to map the distance from the satellite to the surface of the ocean, and the mass of a topographic high in water, such as an underwater mountain, has higher gravity than the surrounding area. Therefore, the water tends to pile up on top of it, and this can be observed by the satellite. When you remove waves, tides, and other oceanographic effects from the water height, anomalies reflect the bathymetry of the seafloor. So here on the left, you can see the JSON-1 satellite, which was used in conjunction with another to produce one of these large-scale gravity maps of the ocean floor. And the map here is actually a gravity map. So if you were to compare this to a bathymetric map of the seafloor made with a shipboard echosounder data, you'd see that the maps are actually really quite similar. I also mentioned earlier that 0.05% of the ocean floor has been mapped at meter scale resolution. Maps of this resolution are created using underwater vehicles equipped with smaller echosounders. So on the right here, I've got a picture of an autonomous underwater vehicle called Sentry. Sentry is autonomous because it's programmed in advance of a dive with the coordinates to map. It's then deployed off a host ship, and it's not tethered to the ship in any way. It's able to produce really high-resolution maps simply because of its ability to reach the near sea floor. Although one of the drawbacks of creating maps using AUVs is that while they provide optimal resolution, they're unable to map really large areas of the seafloor in a given dive because they're limited by battery life. So, while underwater vehicles are fantastic for mapping the seafloor at high resolution, they have many other capabilities. For example, Sentry here is equipped with sensors which measure the physical properties of the seawater, and it's capable of being outfitted with more specialized sensors should a scientist be interested in adding one of their own. Sentry also has a down-looking camera and can take really high-resolution photos of the seafloor, but the best thing about these underwater vehicles, I think, is that they are quite abundant. So Sentry is an autonomous underwater vehicle because it's not tethered to the ship in any way. Alternatively, we have remotely and human-operated vehicles. Remotely operated vehicles, such as the ROV Jason, are tethered to the host ship with a fiber optic cable and rely on a team of operators to pilot, navigate, and monitor the vehicle at all times. The operators work on board the ship in an area called the control van. Jason in particular has a number of high-resolution cameras, not only for the purpose of piloting the vehicle, but also for scientific investigations. And Jason is also fully capable of being outfitted with a variety of sensors for scientific purposes. ROVs are used for a wide variety of scientific investigations, and for this reason, perhaps their greatest advantage is their endurance. Because they are tethered to the ship, they're not dependent on battery life and are capable of remaining in the water for days at a time, which provides scientists with days worth of data for each dive, and we like that. Human-operated vehicles, such as Alvin here, are submarines which carry humans to the seafloor. Here I've posted a photo of a selfie that was taken on a cruise I was on a couple of years ago, and if you look really closely, you can see, oh, my mouse is stuck. You can see in this porthole window a man's face. And so this is Dan Fernari, who is actually the mastermind behind the Alvin selfie. Alvin in particular is capable of bringing 3 people to the ocean floor for about 10 hours at a time, so 2 observers and a pilot. And like Sentry and Jason, Alvin is also capable of carrying a wide variety of sensors to the seafloor, and it's highly adaptable depending on the survey goals. I have been extremely fortunate to work with each of these vehicles and their fantastic team of engineers. And in fact, the photo of Sentry on the far right was also captured on a cruise that I was on during the same time as the Alvin selfie photo. And this photo was taken during a recovery, and you can see that Sentry has a face. So this cruise took place over the entire month of November, and we missed Thanksgiving. So an aspiring electrical tape artist and Sentry engineer, Justin, decided to boost morale by dressing Sentry up as a turkey during that cruise. And it was pretty fun. So each of the vehicles have advantages and disadvantages, and really determining which is most practical is dependent largely on the survey goals. I will say that ROVs such as Jason and HOVs such as Alvin have one major advantage over Sentry: manipulator arms. So both Jason and Alvin have mechanical arms which in many ways resemble those of human arms, which can be used for a variety of purposes. All right, so here we can see Jason is collecting hydrothermal vent fluid samples for geochemical analyses. And in the far right, you can see Jason is being used to actually rescue a moored instrument was trapped in a lava flow. And on my most recent cruise to the axial seamount, the Jason crew were very, very kind to give me the opportunity to try and pick up my own rock sample. So this was taken in the control van, which is on deck of the ship. And I will say to this day, this is one of the coolest experiences I've ever had, and I am very grateful for it. So each of the vehicles, so Jason and Alvin, they have a basket which has a pretty high payload. So you can use that space to bring instruments down to the seafloor, or you can use it to recover instruments from the seafloor. And you can use it for collecting samples such as rocks or animals, or even fluid samples, and you can bring it back up to the ship with you for further analyses. And I guess since we brought it up, another really fantastic way to observe the seafloor is to bring instruments down to the bottom. So here I've highlighted just a few seafloor sensors that I'm interested in. So we've got an ocean bottom seismometer here on the far left, which is used to detect earthquakes, a hydrophone in the middle, which again is used to detect sound. And while hydrophones weren't the best tools for navigational purposes in the early 1900s, they're really fantastic for picking up on and locating earthquakes, volcanic eruptions, and even marine mammals. So in this photo, you can see my friend Matt and I are having one last conversation on the hydrophone before we send it to the seafloor. Get it? Because it's a hydrophone. I guess it's not really that funny if I have to explain it, but I thought it was clever. And anyway, you can see on the far right, again, me being pretty goofy, and I'm acting as a scale bar for a bottom pressure recorder. And bottom pressure recorders are basically used to calculate the deformation of the seafloor. So each of these instruments are attached to an anchor on one end and then to glass balls on the other. And the glass balls provide buoyancy. They're deployed over the side of the ship for a number of years, determined either by the battery life or funding, and recovered on a subsequent expedition. They each contain an acoustic release, which when triggered, allows for the instrument to drop the heavy anchor and the glass balls bring it back to the surface for us to recover. And the style of periodic instrument deployment and recovery is frequently called a campaign-style survey. And while this technique is still utilized in oceanography today. All right, so I've talked quite a bit about a short history of ocean observing, but trust me when I tell you that this is in no way an exhaustive description of the advancements made in ocean observing, and I'd argue that this was a very short history of ocean observing. So we're pretty caught up to the modern day at this time. So I want to switch gears and talk about the current and future state of the field. We've come a really long way in quite a short period of time. And I'll remind you that we hadn't even discovered plate tectonics until the 1960s, and that the first consecutive map of all the Earth's oceans wasn't published until 1977. And despite the speed at which the field has advanced, we're still facing some logistical challenges with observing the seafloor. For one, many of the observations that we've talked about provide only a brief snapshot of an evolving system. For example, bathymetric surveys provide maps of the seafloor for a specific moment in time. If a volcanic eruption occurs, we have to perform an additional survey to measure the changes of the seafloor, such as new fresh lava flows or fissures that have opened up. Likewise, using a vehicle provides only a snapshot and over quite a small area. And of course, anytime we're required to use a ship for an investigation, and certainly a vehicle, we start spending money, and lots of it. The use of ships and vehicles is also highly weather dependent, as we don't want to risk losing an instrument or a human at sea. And another logistical challenge that we face is the issue of resolution. So it's relatively easy to produce a large bathymetric map or interpret data for large areas at the seafloor. We just have to rely on very low resolution data. And alternatively, we can produce really high resolution maps or data sets with high spatial coverage. It's just logistically challenging and expensive to survey a large area in that way. Fortunately, some really bright scientists have found creative ways to circumvent some of these logistical challenges. Earlier in the talk, I highlighted an article called Undersea Cables Transmit 99% of International Data. So here, what you're looking at is a map of the many cables which are transmitting 99% of our international data. All right, so again, undersea cables were first used for the purpose of telegraph communications in the North Atlantic. Unfortunately, these cables were subject to wear and tear, and once damaged, were really unusable for communication purposes over great distance. But scientists quickly realized that they could use the damaged telegraph cables to power instruments on the seafloor and transmit data back to land. And this allowed for a shift from the campaign-style instrument deployments to long-term deployments, allowing scientists to easily begin collecting measurements at a given location for longer periods of time. While I won't argue that these methods are currently cheap, I will tell you that collecting data in this way eliminates the need for an expedition every year or two, which eliminates some of the time and the financial burden of an expedition. It also means that data collection is not dependent on weather conditions and that expensive vehicles or humans are not at risk. Perhaps most importantly, at least for me, the cabled instruments are able to provide access to data in near real time. So here are a few examples of cabled instruments which are a part of the most advanced submarine volcano observatory on Earth, and that's the Ocean Observatories Cabled Axial Seamount Array. Again, we have here an ocean bottom seismometer which detects earthquakes. We have a hydrophone that detects sound and a bottom pressure recorder which we're going to use to calculate deformation of the seafloor. And we're going to come back to the bottom pressure recorders again, but let's move forward a little bit. So the Cabled Axial Seamount Array is an array of cabled instruments located about 500 kilometers off the coast of Oregon. And you can see that the cable is making landfall here in Pacific City, and it spans the length of an entire tectonic plate. So you can see it comes out here to the axial seamount, which is on the axis of the Mid-Ocean Ridge Spreading Center here. So this is the Juan de Fuca Ridge. Over here is the Pacific Plate, and here you've got the Juan de Fuca Plate. And if you look at this zoomed in area, you can see the axial seamount volcano here. So let's zoom in a little bit. If we zoom in to the axial seamount, we can kind of see the outline of a caldera volcano here. And this map is actually showing the locations of a variety of instruments that we have deployed on the seafloor. And we're going to come back to this, but first we're going to have to shift gears for a second and talk a little bit about volcanoes. All right, so axial seamount, can you guys, I just want to make sure, if anybody's unmuted, are you seeing this black bar here? I want to make sure everybody can see the figures.
I can see it.
Melissa, I'm going to assume that's fine then.
Yeah, I mean, I can see your figure. I don't know, you're talking about a black bar.
Okay.
I'm not
yeah,
sure.
I see something over it. I just want to make sure that you guys were able to see that. Okay, fantastic. All right, so axial seamount is a very active caldera-style volcano. So caldera volcanoes are forming when magma is erupted from a magma reservoir, and the roof overlying that reservoir actually subsides into the space that's left in the chamber. So axial caldera is really prominent. It's got 100-meter walls that are forming this caldera shape, and the caldera itself is about 8 kilometers long in this direction and 3 kilometers long here. An axial is at the junction of a mid-ocean ridge spreading center, so where the plates are actually moving apart from one another, and a hotspot volcano. So there's additional melt being supplied from below. And you can actually see here the north rift zone of the mid-ocean ridge and the south rift zone of the mid-ocean ridge are overlapping in the caldera. While most volcanoes erupt pretty infrequently, axial has a very high melt supply because of its location at a mid-ocean ridge spreading center and hotspot intersection. And in fact, humans have observed 3 volcanic eruptions from axial seamount in its 30-year monitoring history. One in 1998, another in 2011, and that produced the blue lava flows here, so that outlined in blue, and another in 2015, which produced the lava flows outlined in green, and this actually extends much farther north as well. Axial is well studied for a number of reasons. Its close proximity to port cities on the coast of Oregon make it an ideal natural laboratory, as it only takes about 24 hours to reach it via ship. It's an extremely active volcano, and it has 3 hydrothermal vent fields, so it's got Ashes, Chasm, in the International District. And these considerations made axial Axial Seamount an ideal location to house the Ocean Observatories Initiative Cabled Axial Seamount Array. An axial seamount is now certainly the most well-monitored submarine volcano on Earth, and arguably one of the most studied volcanoes on the planet. All right, and Axial is actually an extraordinarily special volcano from the perspective of a volcanologist, because until very recently, it was the only volcano on Earth to have an eruption which was accurately forecasted based off of deformation data alone. Oops. All right. So you might know that on land, volcanologists commonly use observations from previous eruptions to assess unrest and potential for eruption of a volcano exhibiting signs of unrest. Frequently, volcanologists rely on physical signs of unrest, such as deformation of the ground's surface, which occurs as magma migrates and as magma reservoir expands. On land, volcanologists rely on satellites and on GPS to actually measure the deformation of the Earth's surface overlying a magma reservoir. And frequently, but not always, eruptions are preceded by large amounts of uplift, and sudden changes in uplift can alert a volcanologist of impending eruptions. Scientists also rely heavily on earthquakes to assess eruption potential. As magma migrates through the crust, it breaks rock, generating earthquakes. Both earthquake frequency and magnitudes tend to increase from base levels in the lead up to an eruption, and this is also a key indicator for volcanologists that a volcano might experience an eruption. So sometimes volcanic eruptions appear to be triggered by a certain event, either large amounts of uplift exceeding some threshold or a high magnitude earthquake, and this finding seems to hold true to the Earth's seafloor as well. We certainly use ocean bottom seismometers to detect earthquakes on the seafloor, and we're also able to use hydrophones to detect earthquakes as well. Unfortunately, we can't use satellites to measure deformation of the seafloor over reasonably short timescales, and we certainly can't use GPS. Instead, we use the instruments I mentioned earlier, the bottom pressure recorders. So how do we measure deformation of the seafloor using pressure? I'm going to ask you to excuse my hokey conceptual diagram here, but if we imagine a bottom pressure recorder is sitting on top of the seafloor crust, we can understand that the pressure that's being exerted on that sensor is due to gravity and the mass of the overlying seawater. And in fact, the pressure on the sensor is related to the density of the seawater multiplied by the gravity and the height of the water depth. So, as the seafloor inflates, maybe due to expansion of a magma chamber, the water depth decreases, and thus the pressure acting on the sensor is going to be much lower. And if the water depth is larger, and thus the pressure on the seafloor increases. I'm going to say that again. As the seafloor inflates, the water depth decreases, and the pressure acting on the sensor is low. If the seafloor sinks, as it would following a volcanic eruption, the water depth is going to be higher, and the pressure on the seafloor is going to increase. So this was exactly the motivation for instrumenting axial seamount with pressure recorders following the discovery of active hydrothermal venting in the late 80s. In 1997, scientists deployed 2 bottom pressure recorders on the summit of axial seamount. In 1998, they were alerted by a hydrophone array of large earthquakes and potential volcanic eruptions. After returning to collect their instruments and download their data, they saw something that looked like this. So this top panel has been converted from pressure to depth. You'll see that here, it's vertical displacement. And the bottom panel here is actually temperature. So if you look, you can see a wide variability in depth that is occurring quite quickly in the sequence. And these are tides. So the black data here is actually changes in depth with the tides still in it. Now, if you filter out the tides, you get this red signal here. And that is deformation of the Earth's seafloor. So again, the bottom panel is showing temperature. And if you look at these data, you might already be thinking it, but it shows something quite interesting. A volcanic eruption. So scientists were extremely lucky to have captured this eruption during the earliest deployment on the summit of axial caldera, and this has sparked decades of deformation experiments to occur at axial. All right, so here we have plotted the deformation data again in the top panel. This is exactly what I just showed you. It's just we have a longer time series here. I've covered it up with this block that says time, so it looks much shorter. The panel below is showing the monthly earthquake count as determined by a hydrophone array off the Oregon coast known as the SOSIS array. After recovering their instruments following the 1998 eruption, scientists had to wait about 2 years before redeploying. So you can see that here in a data gap. Nevertheless, monitoring continued and inflation was recorded. So you can see some inflation occurring here. In 2006, unfortunately, the SOSUS array, the sensors that were most useful for monitoring axial, went offline, but they were replaced in 2006 by some NOAA hydrophones. And almost immediately, scientists realized that the earthquake rate was actually increasing quite rapidly. So in 2011, another volcanic eruption was recorded. And it was at this time that Bill Chadwick and Scott Nooner noticed something really interesting. And that is that the volcanoes seem to have a threshold at which the eruptions were occurring. And you can see that here. It was about 3.4 meters. That amount of deformation occurred before the 1998 eruption, and then again at the 2011 eruption. So then they did something really interesting. They proposed that the next time the volcano will erupt would be when the deformation exceeded that threshold of 3.4 meters again. And they continued monitoring. And they noticed that the deformation, or the rate of the deformation that was occurring much more rapidly than they'd previously seen in the 2011 and 98 eruptions. And they also noticed from this NOAA hydrophone array that the rate of earthquakes was also increasing. And so they had to push forward their predicted date again. And I would love to show you the website where they made this forecast. Unfortunately, it is a government website and it is offline right now. But in 2015, Bill Chadwick and Scott Nooner were correct in their forecast, and the eruption did occur almost exactly when they said it would. It did exceed this threshold of 3.4 meters, and that was pretty interesting. It was the first time that a volcanic eruption had actually been forecasted based off of deformation data alone. So again, a very special volcano for that reason. Now, I also want to point out something special here, and that is that in November of 2014, the axial cabled array came online. And then in April of 2015, this eruption occurred. So we got lucky again. We put these new instruments on the seafloor, and just as in 1998, they almost instantaneously captured a volcanic eruption. But again, one of the great things about the OOI is that these sensors are cabled to land, and so we're able to receive that information almost instantaneously. There's a short lag of a few seconds, but the data is real time otherwise. So allow me to share with you a few more fantastic coincidences. So after the array went online in November, my advisor, Trish Gregg, who was looking for a tenure track position at an institution where she could develop a robust volcano eruption forecasting framework, interviewed and was hired at the University of Illinois, Urbana-Champaign. Given that Illinois houses the fastest supercomputer on a university campus, she understood that they had the equipment she needed to make her research goals possible, and she accepted the position. In April of 2015, axial erupted, Bill and Scott's forecast was validated, and the eruption was recorded by the OOI. In August of that year, I started my PhD at the U of I, and I was working with Trish Gregg. In June of the next year, Trish received funding from the National Science Foundation to develop a real-time forecasting strategy at Axial, and I inherited the coolest dissertation project ever. So, let me take a drink. The forecasting method that my advisor had become really interested in is called the ensemble Kalman filtering approach. And it's an approach that has been widely used in the fields of climate and weather forecasting, but never before for forecasting volcanic eruptions. So the ensemble Kalman filtering like methods, or ENKF, these are even used in the GPS units you have to navigate your car. And this approach is a data assimilation technique where numerical models are combined with data to improve the model estimates, and the model estimates can then even be used to improve the quality of data or to inform you where your models might be lacking and where you might want to add additional instrumentation. So the way this works is that we start with a best guess model ensemble, which is heavily informed by previous studies. We then run the models forward in time, and then when real data becomes available, so we're currently focusing on using that bottom pressure data, We combine it with the forecast ensemble and the ENKF analysis to provide an updated model forecast. We then continue to iterate using this technique and use it as more data is coming in. And eventually, we are able to constrain parameters such as magma reservoir size, location, and pressurization. So then we use these statistical outputs from our forecasted models in conjunction with finite element models to calculate stress, strain, and various types of failure in the host rock surrounding a reservoir. Let me show you what that looks like. So here you can see an example of what model calculated failure looks like. These are model outputs that I published for a very different type of volcanic system. This is for a large caldera system called the Taupo volcano. But the idea here still holds. So failure tends to accumulate in the roof overlying a magma reservoir as the reservoir inflates. Eventually, when the failure reaches the reservoir from the roof, so you can see when we start to connect the reservoir to the roof, we consider the system to no longer be stable, and we suggest that an eruption is likely to occur. And the time at which that eruption occurs becomes the forecasted eruption date. So, the availability of deformation data spanning 3 historic eruptions at Axial Seamount and the recent development of the OOI's Cabled Array make Axial Seamount an ideal target for launching a near real-time eruption forecasting study. So we aim to use the historic autonomous BPR data from Axial Seamount to actually hindcast the previous eruptions using the ENKF technique. So this essentially means that we're going to run the data from 1998 to the present and pretend we don't know the dates that the volcanic eruptions occurred. We'll be able to test the accuracy of our statistical models in this way, and then we'll also be able to use them to understand the mechanics, what's actually happening to trigger the eruptions at Axial Seamount. We'll then develop a handshake with the OOI's real-time data and the U of I's Blue Water supercomputer to develop the first real-time eruption forecasting technique using the ensemble Kalman filtering approach. And there are 3 pretty critical stages that we have to reach before we can actually develop the real-time forecasting, and we're currently finishing up with stage 1. For that reason, I don't have updates to a forecast for you, but I can highlight a few other cases where this technique is being used. So currently, my lab group is the only one in the world using ENKF to forecast volcanic eruptions, and my lab mates are using it to study various terrestrial systems. So Jack is using it to study the Okmok volcano in Alaska. Yan is using it currently to forecast eruptions of Indonesian volcanoes, and my advisor, Trish Gregg, successfully forecasted the 2018 of Sierra Negra volcano in the Galapagos using this technique. As you can imagine, our group is very, very excited about this right now, and we're planning to start running our first model runs for Axial Seamount on the Blue Water supercomputer in just a few short days. So stay tuned, and we can hopefully give you some exciting updates on the state of Axial very, very soon. So with that, I need to thank a lot of people. I need to thank my advisor, Trish Gregg, of course, my lab group. You can see us here, not pictured as Valentina Romano. She's a postdoc with our group. And also, I need to thank the members of the Axial cruises that I've been on in the past 2 years. So this was our most recent expedition this past summer on board the Kila Moana, and this was the year before on the Roger Revelle. So thank you to all of the scientists who participated, to all of the scientific support staff and the crews of these vessels. I've certainly learned a lot from everyone I've had the opportunity to work with. Thanks to the people who participated in the Oasis expedition in 2016. This is the cruise that my advisor was the chief scientist for. It's also where we got those fantastic videos. It's a compilation video of Alvin dives that occurred on this cruise. So thank you to Scott Nooner. He's on my thesis committee. He's at the University of North Carolina, Wilmington, and to Bill Chadwick, who's with NOAA PMEL. I've certainly learned a lot from both of them. And I want to thank you guys again for tuning in and listening to me talk about my research today, and I wish you all the best of luck with the National Ocean Sciences Bowl. So thanks.
Thank you, Haley. We appreciate that presentation. So one of the benefits to participating live in the webinars is that you get to ask all the questions that you've been thinking of since the start of the presentation. So this is the time to go ahead and start typing them into the chat box. And again, I'll read them aloud for Haley to answer.
All right, thank you.
Okay, we'll just give everybody a minute or two to think about their questions.
Sure.
Any questions? We have one about the recording. Yes, we are recording, and we will post it on our YouTube channel later this afternoon, and then we'll circulate it to everybody. Okay, so one question is, can you review when the seafloor inflates and when it doesn't using bottom pressure recorders?
Yeah, when the seafloor inflates and when it doesn't. So let me go back to that really quickly. That little hokey conceptual diagram that I made. All right. So this is just a conceptual diagram here. Basically, this is meant to resemble the water depth. So at axial seamount, the summit is at about 1,500 meters depth. So the height here should be about 1,500 meters. This black area is kind of what I chose just to represent the seafloor, but the seafloor is not stable. It's constantly moving up and down. And it can move for a couple of reasons, but at axial seamount, the reason that we know the seafloor is inflating is actually because there is a rather large magma chamber in the crust. And this magma chamber is being fueled from below by influx of new melt. And as it starts filling the magma reservoir, the reservoir inflates. And as a result, the rock surrounding that reservoir also inflates. So, sorry, my mouse has a little bit of a lag in it. So if we have a bottom pressure recorder sitting on that crust that is moving up and down, the thing that is changing in this equation, I'll go back to it. So here's our seafloor in its undeformed state. Here it is again. You'll notice that the height of the water is changing, right? So the load on the seafloor, as caused by that change in water depth, is changing the pressurization on the sensor. So basically, the pressure on the sensor is the result of the density of the seawater, gravitational loading, and then that water height. So when we decrease the water height, we're decreasing the pressure on the sensor, which then we can convert to depth. Does that make sense?
I guess so. No follow-up question. Yes, they said yes. Thank you.
Okay, awesome.
Someone else asked, can you describe how you relate this work to the study of volcanoes on land?
Yeah, absolutely. So we have fantastic monitoring agencies that are monitoring the largest and the most dangerous of our volcanic systems. And the way that we've traditionally kind of forecasted volcanic eruptions is largely by pattern recognition. So kind of like I mentioned when we were talking about a couple of the methods for monitoring, and these are by no means exhaustive. These are just some of the more physics-based approaches we use. We're looking for patterns. So let's say that we have an eruption that occurred and it was preceded by a large magnitude earthquake by, a matter of hours. So we might be thinking, okay, the next time this volcano erupts, it's going to be preceded by an earthquake that's quite a large magnitude. And once that happens, we know that we have a matter of hours before it erupts again. Now, that's not all people are monitoring for, right? We're still looking at deformation. We're looking at other earthquake activity. We can even use geochemical techniques. We can look at gas emissions data coming from the volcano, or the chemistry of waters that are moving down slope, because that'll change as magma starts to migrate towards the surface. But the reality of the situation is that these volcanoes aren't always going to behave by the rules that we apply to them. So that a rule that we've said, you know, this volcano is going to erupt again when it exceeds some large magnitude earthquake, we can't necessarily validate and verify that because volcanoes are dynamic systems and they're changing very rapidly. There are other factors that could actually trigger the eruption. So this new volcano forecasting strategy that we're using at a couple of terrestrial volcanoes, but also on the seafloor, we're currently using it to try and use a more statistical approach and a more physics-based approach for truly understanding what's happening in the volcano, so that we can provide a more realistic update of the volcanic system state in order to say definitively, yeah, we see that instabilities might be developing in these areas and that could lead to an eruption that might not otherwise be exceeded by that earthquake we're expecting. So that was a long answer to basically say, we're still learning a lot about how volcanoes erupt, and this approach is just a little bit more robust than the pattern recognition approach that we've used for so many years in the past.
Okay. The next question, is there a connection or correlation between activity at axial and activity with the Cascadia subduction zone?
That is a really good question. I will tell you that the two systems are not linked, right? So you shouldn't be concerned, right? Just because we're having these eruptions off the coast at axial, don't be concerned about volcanoes in that area and in the terrestrial realm. It would be interesting to look at just to see if there's any correlation, but I don't think that you have anything to worry about with axial erupting. It's erupting for entirely different reasons than the Cascadia volcanoes are. So it's at a mid-ocean ridge spreading center, and mid-ocean ridges tend to erupt far more frequently than those types of volcanoes do. So those are arc volcanoes that are erupting largely because you have plate subduction going on. So you're subducting a plate, you're decreasing the melting temperature of the mantle, which produces new melts and causes volcanic eruptions in that way. So I don't think you have anything to be concerned about, but I can't definitively tell you that there is no correlation in the two. That would be interesting to look at.
Okay, another question asked if you could go over other AUVs, HOVs, and ROVs that are relevant to seafloor mapping.
I can give you the names of a few, so let's see. I'm wondering if there's an easier way to go back, but so I'm going to go back to this slide. There are a number of other AUVs, ROVs, and HOVs that are used. So these are the three that I've worked with, and they're all operated by the National Deep Submergence Facility at Woods Hole Oceanographic Institution. And so JASON is their ROV. There's a Canadian ROV that's very similar to JASON called ROPOS, and ROPOS was actually used for a lot of the instrumentation at the Cabled Axial Seamount Array. So there are certainly others, and actually there's a lot of use of these types of vehicles in industry as well for oil companies in particular, people who are doing offshore type stuff. But there are a lot of research institutions that have different versions of them, and they all have different depths that they can go to as well. Same with the human-operated vehicles. So Japan has a submarine. There are a couple others in the U.S. Alvin is kind of the oldie goldie. It was developed in the 1960s, and it's been revamped a couple of times. But that tends to be the scientific human-operated vehicle that people think of when they think of a submarine. And Alvin, interestingly enough, I forgot to mention this earlier, has been rated to go down to about 4,500 meters. And actually, we just did another cruise in December. It was the second part of that Oasis cruise. So they went back out to the 820 seamounts in the Pacific Ocean. And that was Alvin's last tour before it's revamped again. And they're going to work to rate it so that it actually can dive to 6,500 meters depth. Sentry is just another autonomous underwater vehicle, and this again is operated by NDSF. We had another AUV on my last axial expedition called the D-Allen-B that's operated by Mbari, and they were used for similar purposes. So we're going out there to collect repeat high-resolution bathymetry of the area to try and understand deformation of the seafloor. I would argue that most of these vehicles are used for similar purposes, but also highly adaptable. Again, many scientists are actually developing their own sensors and bringing their own instruments down using the different vehicles. And so they're very adaptive depending on what your survey goals are, what you need to measure, what you're interested in. Was that helpful?
Yeah, let me know if you have a follow-up to that question, and if anyone else has any other questions, go ahead and type them in.
Promise that's a liqueur.
Yep, the question about the AOVs, they said thank you for taking the time to explain that.
Yeah, of course.
Any other questions? I would ask if you could just give a real brief sort of description of how you came to get into this line of work. One of the things that the National Ocean Sciences Bowl likes to do is try to explain to the students who participate how they can get involved in ocean science related careers. And obviously having you working in the center of the country does make that, you've made that stretch from working inland but working with the ocean. So if you could just go over really briefly how you got into this, I would appreciate that.
Sure, absolutely. So when I was an undergraduate, I did my undergraduate degree at a school called the College of Charleston, and that's on the coast in Charleston in South Carolina. And when I was there, I actually got very interested in plate tectonics. And I had this professor who agreed to take me on and let me do a little research project with her. And we were trying to understand how Pangaea broke up. And so I started using this open source platform called GeoMap app. And I was basically going through and I was looking at the orientation of transform faults and fracture zones in the Atlantic Ocean. And I was looking at magnetic data so that I could understand the ages of the seafloor. And I was just really trying to understand any subtle changes that might provide some information about key events that were occurring when the supercontinent Pangaea was breaking up. So I was doing this thesis project. I love plate tectonics, and I wanted to continue studying those types of things. The next year, the same professor turned me on to an internship opportunity in Colima, Mexico, at the Center of Exchange and Research in Volcanology. And I also really loved volcanoes, so this was perfect for me. So I went and I lived in Mexico for a few months working for this volcano observatory and just absolutely got bitten by the volcano bug. But I was refusing to turn down my love of plate tectonics and volcanology. I wanted to do both. I refused to specialize. Well, then I also started taking some courses in my last year at the College of Charleston on seafloor mapping. And I found that I also really enjoyed oceanography and started to understand that my first project using GeoMap app data was actually ocean science. It was marine geophysics. And so I had these kind of three fields that I really, really enjoyed. And I didn't want to give any of them up. I've always resisted that very heavily because I don't want to be so specialized that I can't continue to study all of the things that I'm interested in. So as I was starting to apply for graduate programs, my current advisor, Trish Gregg, had posted this advertisement. She was looking for students, and she had all these amazing projects. So I've mentioned the Oasis cruise a couple of times. Trish had that cruise scheduled, and she was also starting to use this ENKF method to investigate Indonesian volcanoes. And we met and talked about it, and I kind of told her, you know, I don't want to specialize. I want to keep studying all these things. And I was also extremely interested in geochemistry too. So I was just a really eager undergrad. And she was on board for that. She was excited to have a student that wanted to do all of these different things. And so I came here and I started a project that was trying to understand what effect any kind of stress, so things related to tectonics, what effect that might have on triggering volcanic eruptions. And we were also preparing for the Oasis cruise at the same time and getting really excited about oceanography. And she was like, Haley, check out, you know, the OOI, an axial seamount. I think this could be a really cool volcano to use data assimilation at, use the ensemble common filtering method at. And so that was during my first year of graduate school. Trish put it in an SF proposal to use the ensemble common filtering approach to start forecasting eruptions of axial, and she got it funded. And me being the student that didn't really want to specialize and I wanted to study oceanography and volcanoes and all of these crazy things, she put me on it. And I've been combining all of my passions ever since. So I would just say to any student that's interested in this kind of stuff, say yes to every opportunity you're given. I've certainly done that. Anytime that I hear of something that I can participate in and it sounds remotely interesting to me, I just say yes. And you meet people in that way and you get connected with other opportunities doing the same thing. But also, and maybe this might not be the best approach, but if you have many interests, don't buy into that pressure to specialize and confine yourself to one field of study.
Well, thank you for going through that. I will note one of the things that we say a lot with the National Ocean Sciences Bowl, especially with teaching kids about ocean science, is that it is so interdisciplinary that it's a great opportunity if you have an interest in biology and chemistry to combine them. And then at the same time, when you're in the field, you get to work with geologists and people in physical oceanography. So it's a great STEM career to sort of move into if you're at all interested in oceans. And we had one of our coaches from Kentucky say, thank you. She's very glad for an example of someone inland studying ocean science. So again, thanks for going through that. So,
well, thank you guys very much.
So I think those were the last questions we got. So we're going to end the webinar from this afternoon. We even had somebody from Maui participating. They said thank you. So just to remind everybody again, we will have the recording of this webinar up on our NOSB website as well as our YouTube channel. I'll try to get that up by this afternoon. We do ask, obviously, that you share these. This is a resource. That's part of the reason why we do this for the NOSB coaches, but also any other interested educator. So definitely share these amongst your colleagues. Obviously, share them with your NOSB teams and students if they're getting ready to compete in 2 weeks. And as always, if you have any comments about the webinar, feel free to email nosb@oceanleadership.org. We'd love to hear back from you and how these webinars actually do help you and your teams prepare. So I want to thank everyone for joining us on this Friday morning/afternoon, and I hope you all enjoy the rest of your day. Thanks again.
Thanks.